What's going on, you guys? So today we're doing symmetric tree. We're given a binary tree. We want to check whether it's a mirror of itself. So for example, this binary tree, if you think about a line going straight down the center and you fold one side onto the other, then they'll be equivalent. So you're going like this. If you fold it and then you've got the same thing, then it's symmetric. Like my hands here, right? I can fold them in half and everything lines up. So let's think about this. So if it is a mirror, right? So if it is a mirror, then we'll return true. So what do we want to do? How do we want to compare our left and right sides? So if the left and right side are mirrors, then we're going to return true. So we'll create a function isMirror. It's going to have a left and right. And what are we going to do with our left and right? Let's see. So it's going to return a Boolean. This will be a tree node. And so will the left. Okay, so let's think about how we're going to compare the left and right nodes. So if they're null, so if left equals null and right is null, we'll return true. What else? Let's think. So the values have to be the same. So let's see. So left.val has to equal right.val. What else? So let's think about this. So left.left has to equal right.right. And left.right has to equal right.left. So let's see here. So isMirror left.left and right.right and isMirror left.right and right.left. Okay. Trying to think about what would happen if one is null and the other is not null. So let's think about that case. So if they're both null, we return true. If one is null, what happens then? So if one is null, this is going to return false, right? Okay, so that's taken care of. Cool. Okay, so let's take this. So we'll say if root is null, we'll return true, I guess. Not sure what they want us to do if we just get a null value. But we're going to return isMirror. If the left and right hand sides are mirrors, then we're going to return true. Root.left and root.right. Okay. And let's think here. So if they're both null, we're going to return true. Otherwise, if their values are the same and their branches are mirrors, then we'll return true. So we're doing, let's see, left dot left and right dot right. That's our first pair. And then left dot right and right dot left. That's our second pair. Okay. And we just do that recursively until it gets to the end, these leaf nodes. And it's going to return true for those guys. Okay. So let's give that a shot. Oh, let's think about space and time complexity. So let's think here. It goes from the root node, and then we look at 2 and 2. And then we look at 3 and 3, and 4 and 4. So it's touching every node. So we have to digest every node in the tree. So it's O of the number of nodes in the tree. And space complexity, so there's recursive call stack, right? For every isMirror call. We're going to call isMirror on every single node in the tree. So it's O of n space and time complexity. All right, let's see if this runs. Oh, what's the problem here? Oh, right. Oops. Okay, so technically this could be null, so we need to note that here. Okay. Okay, so that's a recursive solution, O of n's space and time complexity. Now let's think about a iterative solution that would be that might do a little bit better on space complexity. So let's think about this. Okay. So an iterative solution, what can we do here? So we could create a stack, and we could push pairs to be compared onto the stack. So for example, we could have a stack equals this, and then we'll push 2 and 2, and then we'll push we'll compare 3 and 3 and 4 and 4. And if we do all these comparisons, we get to the end successfully without hitting anything, we'll return true. We'll return false if any of these pairs are not equivalent. So let's see how that's going to be done. So we're going to say we're going to create a stack. It's going to be a stack of pairs, and it's going to hold 2 tree nodes. Okay, so we'll push The first pair will be root.left and root.right. We'll say while stack is not empty, we'll pop the respective values from the stack. And we'll do some comparisons. So what do we want to do? So if they're both null, so if left is null and right, here we can reuse some of those conditions from our recursive solution. If left and right are both null, then we're good. We can continue. And now if left, now that we know that both of them are not null, if one of them is null, then we want to return false. Or if like we get, for example, all right, let's see what our stack would look like for this second example. We'll say stack equals, we're going to compare left and right, so 2 and 2, and then we're gonna pop excuse me, we're going to push left.left, which is null, and right.right, which is 3. And we're going to push left.right 3 with right.left, which is null. So these are our two problems that we'll get in this stack. And so if either of these are null or the value does not equal, if left.val, I guess we have to do that here. Well, that's not null. Okay, so that's our check. We'll return false if either of them are null or the values are different. Okay, cool. And now we're going to push, what are we going to push? We're going to push the pairs we want to compare. So we want to compare left.left with right.right, and we want to push left.right with right.left. Okay. And so eventually we're going to push null and null, and it's going to continue, and the stack is going to become empty. If we get to the point where the stack is empty, we know that we've gone through all the checks successfully, and it's true. Okay, let's think about space and time complexity. So it's reaching each node in the tree. So it's O of n time complexity, where n is the number of nodes, and space complexity. So the size of the stack it's O of n. We have to put every value into the stack. Okay. Well, let's think. So each time we enter the loop, we pop 1 and we push 2. So we're adding 1 through each loop of the stack. So for each level of the tree, there's one additional increment to the size of the stack. So the space required is like the depth of the tree, which may be less than the number of nodes. So a little bit better than the recursive, where it was you have to call isMirror on every single node in the tree. Okay, see if this works. Okay, so because root could be null, we have to do a null safety check. Okay, you guys, so space a little bit worse than the recursive solution. That's interesting. Yeah, so we get these variations in memory, so it's hard to tell how it's doing in memory, but it seems like it might be doing a little better because each call, each loop through, we add 1 to the stack. And we're looping through, each iteration corresponds to one level, a depth of 1, right? So first iteration, we're at depth 2, second depth 3. Okay. All right, you guys. So that has been Symmetric Tree. Stay tuned for